All right, so we have one detail to kind of clean up out of chapter 11 before we move on to chapter 13. And it's the concept of osmotic pressure. Now, osmotic pressure is not a terribly difficult concept if you know what osmosis is. Osmosis is the movement of solvent particles from an area of high concentration to low concentration. Any of you that have taken biology in the past have some kind of understanding of osmosis from a cellular standpoint. You think about a plant or an animal cell, water is exchanged from that cell membrane to the outside of the cell or to the inside of the cell, depending upon the environment. So with osmotic pressure in particular, we talk about a barrier that does not allow the passage of solute particles. Another term for that is a semi-permeable membrane. So in this scenario, what we are ultimately looking at is we've got a barrier. That barrier allows certain kinds of materials through, in particular small molecules, and other materials have to stay outside. Usually that means that solute particles, things like sugars, salts, other kinds of things, are too big to pass through the membrane. But water molecules are capable of. What osmotic pressure is this process of osmosis occurs on its own. Naturally occurs without any outside interference. Take a look at this picture here. We can see that the net flow of substance is going from the solvent side to the side that has more solute. Water molecules are going in the direction from right to left because there are fewer water molecules on this side than on the other side. Now, what osmotic pressure does is, let's say that we exert some kind of a force on the solution to try to push back those water molecules and make it so that they never cross over. The amount of pressure that is exerted to reverse that flow, to prevent that flow from occurring, that is what we call osmotic pressure. So if we exert such a pressure that none of this flow occurs, and everything stays exactly the way that it was, that is called the osmotic pressure of that solution. Now, the osmotic pressure of a solution is dependent upon a couple of things. It's dependent upon the concentration of the solution. More concentration means more osmotic pressure is required. And the second thing is temperature. And both of those are direct relationships. Now, osmotic pressure doesn't have a ton of direct applications for us. There are a whole lot of things that we can talk about in relation to osmotic pressure. But the concept overall is important to a couple of really key processes. One of those, very common application of osmotic pressure, is something called reverse osmosis. Now, in reverse osmosis, what we have in there is, if we take that osmotic pressure, instead of just applying directly the osmotic pressure, we actually exert a greater pressure than the osmotic pressure. What will start to happen is that we will see water molecules going in the reverse direction of the way that they should. And on the other side, what we will end up getting is a more pure water product on the other side. So any kind of water process, if you look on the back of the label and it talks about a reverse osmosis water process, this is what they do. They basically take the water and they run it through these tubes. And they exert such a great pressure on the water that they force the purified water to go into these hollow tubes and get pushed through. And it leaves behind any of the impurities that might be associated with the water source itself. So take, for example, Aquafina. Does anyone know where Aquafina's water source is? It's tap water. Aquafina is tap water that has gone through a reverse osmosis process, I think 5 or 6 times. That's all it is, though. It's not a mountain spring. It's not any kind of natural resource. They literally take tap water, push it through a filter a bunch of times, and sell it as purified water. Now, what's interesting about most of those cases, Aquafina is not the only one that does this. Most of your bottled water is done in this way in some kind of form or fashion. But they actually add minerals back to the water after the fact, because otherwise the water doesn't taste very good. So they'll add some kind of minerality to it, various different forms, so that the water tastes the way that water should taste. But yeah, if you read your labels carefully, you'll find that this is the case in most places. Now, there are some spring water sources out there. I'm not going to deny those. And if you read them carefully, they'll say something like bottled at the source or something along those lines. But most bottled water that you buy, in particular the really cheap bottled water that you can get at store brands, gas stations, those kinds of things, it's just water that's been pushed through a filter a number of times. So that's one really common application. Now, this started as a process for desalinating water. That is, you use a good enough filter, you can take salt water that you would find in an ocean or a sea and turn it into water that people can drink. And especially in really poor countries that are landlocked or only have access to the ocean for water, that's really important to them. But it's eventually made its way to other kinds of more commercial applications. Now, the other kind of application, this is more of a biological example, is in your own body. Your body is a very complex chemical system of a series of solutions and other kinds of substances, all in this general solution that we call blood or cytoplasm, or whatever the case may be. Let's take I'll look at one particular type of cell, your red blood cells. Now, a red blood cell is supposed to look like this first panel. It's supposed to have a kind of a divot in it. That's what normal red blood cells look like. Now, if you have other kinds of health issues, for example, if you have sickle cell anemia or even sickle cell trait, your blood cells do not quite look like this. They do have some differentiation of shape, which is why people with those particular conditions usually have to be pretty aware of their surroundings and their environments, especially in high altitude kinds of situations where there are lower concentrations of oxygen in the air. But this is what a red blood cell is supposed to look like, at least in most cases. It's supposed to have that divot in it. And in your blood, you have what we would call an isotonic situation. That is the concentration of all of the things that make up your blood, that make up your body conditions from a concentration standpoint. It's the same inside the cell and outside the cell. And so, yes, there is an exchange of materials. Your body takes in water, releases water, takes in minerals, ions, releases those, but it occurs at an equal and opposite rate. If I were to extract a red blood cell and put it into a hypotonic solution, that is a solution like pure water, where there's no minerality to it, there's no concentration to it all, it's just water. Osmosis would tell me that the water that is at a higher concentration outside of the cell would start to make its way into the cell where it has a lower concentration. And so water would start to flow into the cell itself, and that would cause the cell to puff up and take on this other form. In this other form, it's got a couple problems. First of all, there's a limit to how much water it can take on. Eventually, that cell will burst from all the excess water. The other problem is that at this particular state, it's not as efficient at carrying oxygen or doing any of the other things that it's supposed to do. The third kind of situation is a hypertonic solution. Now, in a hypertonic situation, so for example, a high concentration of sodium chloride. In those situations, you have a higher, greater concentration of solute outside, a lower concentration of water. And so what happens is that the water starts to escape your cells and go to the outside. And as a result, those red blood cells shrivel up and kind of collapse on themselves. And it's for this reason, if you think about it, most of you are nursing or health kinds of majors, right? Okay. If you grab a saline bag and hook it up to someone's IV, what concentration is that saline bag? It's never pure water, right? It's always a very specific concentration. Why is that? Because we're trying to preserve the normal environment of your cells. If I put pure water into somebody's body, the chemistry is not right. The body's going to start to behave poorly toward that. So even when someone's dehydrated, you know, they've been throwing up all night, or they've been really, really sick and they just haven't been able to hold down fluids, you don't just give them pure water inside of the hospital. you give them a saline solution. You hook them up to some kind of fluid solution that has small amounts of minerals dissolved in it, usually sodium chloride. And the reason why? We want to build up their fluid reserves at the appropriate concentration. If we just put water into their veins, they're going to end up having the wrong kind of body chemistry. The red blood cells, their other cells are going to behave poorly. We're actually causing more damage than what was already there. And the opposite is true, but with the same disastrous effects, if I grab the wrong kind of saline bag. If I grab one with a concentration that's too high, it's going to have the opposite effect. It's still going to be bad for the patient, but for the exact opposite reason. It's going to cause their cells to shrink up and decay as a result. So just a little bit there about osmosis and osmotic pressure, just to kind of round out that chapter 11 for us. Any questions about osmosis before we finally, once and for all, put chapter 11 away? All right then. So we're going to move now then into chapter 13. Now, chapter 13 is all about acids and bases. Now, you saw a little bit about acids and bases in your lab last week. You're going to get a little bit more of this information this week as well, as we start to look into not only what acids and bases do, but the kinds of solutions, the kinds of reactions that they can overall take on. So we need to start kind of from a simple standpoint. Basic definitions. What are acids? What are bases? And so from a physical properties standpoint, from a chemical properties standpoint, here are the things that allow us to kind of differentiate the two. For example, we know that acids on the whole, in general, tend to taste sour. Now, that doesn't mean that we walk up to the bottle of hydrochloric acid in the lab and stick our tongue up to it to verify that it's actually an acid. That is, in all accounts, in all situations, a bad idea. But what it does mean is that if we do encounter things in our everyday life that have this particular property, there's a probable cause for that. Why are lemons sour? Well, lemons contain a combination of citric acid and ascorbic acid, both of which acids would taste sour. So we can use that kind of reasoning to help us to figure out when we encounter something in a normal kind of way, what does it ultimately mean? Bases. We know that bases generally taste bitter, and they have a slippery kind of feel to them. Again, that doesn't mean that we go up to the bottle of sodium hydroxide or our bottle of ammonia and put it up to our lips. But in general, we can use that kind of property to help us figure some things out. Why does soap taste bitter if we accidentally get it into our mouths? Why does baking soda or antacid tablets, why do they taste bitter? Why is there such a big industry in trying to make an antacid taste good? Well, because they usually taste bad because there are bases that we're putting into our body to try to neutralize acid. So yeah, they're going to taste bad because in general bases taste bitter. The slippery nature of soap comes from its derivation in the fact that to make soap, we usually have to treat certain kinds of materials with base. Now, that doesn't mean that the soap itself is basic, although it would register on the higher end of the pH scale. But it is a precursor. It's one of the things that happens in the soap making process. You saw this in lab last week. Acids and bases are capable of changing the color of dyes. In particular, you looked at litmus. Acids turn litmus red, bases turn litmus blue. You also saw that in phenolphthalein, base was able to turn phenolphthalein pink, whereas an acid kept it in a colorless kind of state. We also saw in lab, acids will cause corrosion of many different types of metals. Think about the reaction that you did with the, was it magnesium? You had 3 different acids, you dropped in the pieces of metal into each of them. They all reacted, some slower than others, but they all reacted to form these hydrogen gas and some other kind of solution. And we've seen in many cases acids and bases combining to neutralize each other, to basically negate each other's effects. When it comes to defining bases from a chemical standpoint, we're going to explore 2 different theories in particular. The first comes to us from the 1800s. It's called the Arrhenius model. Now, in the Arrhenius model, this is probably our simplest definition. What the Arrhenius model tells us is that when acids come into contact with water, we will see hydrogen ions, H pluses, formed as a result. Now, those H pluses can also come in the form of what we would call the hydronium ion, H3O plus. So it's not uncommon to see that as the product of an acid in water also. Bases tend to form hydroxide ions. And so if you think about the way that we've tried to identify acids and bases, remember back to nomenclature. We talked about acids as being substances that started with H. We've talked about bases as being substances that ended with OH. Those definitions were based upon this Arrhenius model. Hydrogens make H pluses, bases make hydroxides. And for most purposes, for most acids and bases, we can follow this along and be pretty accurate and pretty confident with that line of thinking, that line of reasoning. But there's a big problem with this particular model. And that big problem is that there are many common bases in particular that do not follow the Arrhenius model. And there are some common acids that do not follow this Arrhenius model either. So let's take a look at some of the problems surrounding that particular this particular model of acid-base understanding. First of all, hydrogen ion, H plus, does not exist in aqueous solution. There's no place for it. What happens is that H plus ends up grabbing onto a water molecule to form the hydronium ion. That's why I said oftentimes we will see that hydronium ion in the place of an H plus ion in common chemical reactions involving acids. So when we think about an acid like hydrochloric acid in water, this is the reaction that actually takes place. Hydrogen chloride or hydrochloric acid reacts with water to make the hydronium ion and the chloride ion. This is a more accurate representation of what is going on inside of that solution. And so because of this big problem, while the Arrhenius model does a good job for us helping to identify certain types of acids and bases based on formula, again, starts with H, ends with OH, starts with H, ends with OH. Following that model of, okay, this is what an acid looks like, this is what a base looks like. We needed the ability to expand upon this model. And that's where Bronsted-Lowry theory comes in. Bronsted-Lowry theory, which is nearing its 100th anniversary, defines acid and base based upon the movement of those H plus ions. By definition, an acid is something that is going to donate an H plus ion to another substance. That other substance we call a base. And under the Bronsted-Lowry definition, a base is a substance that accepts a hydrogen ion from another substance. Again, that other substance we call an acid. So under this particular model, every chemical reaction of an acid involves a base as well. Acids and bases coexist at the same time in these kinds of chemical reactions. Now, they don't always end up with neutralization. That's different. But every acid, in order to act as an acid, needs to have a base that it acts with as an acid with. And so this definition of acid-base reaction deals with transfers of protons. So H plus, you will all often hear referred to as a proton under these definitions. Why a proton? Well, again, think about what that means. A hydrogen ion, most hydrogens have one proton and one electron. If it's hydrogen plus ion, that means that the electron is gone, which means I only have the proton left over. So under these definitions, we now can examine acid-base theory under that kind of idea. The H plus goes from HCl to water to make the hydronium ion and the chloride ion. In this situation, hydrogen chloride was acting as an acid, water was acting as a base. And it resulted in two other substances, the hydronium ion and the chloride ion. What the Bronsted definition also allowed, and this is a really important piece, is that it allowed substances like NH3. Look at ammonia. NH3 does not have a hydroxide on it. So under the Arrhenius definition, ammonia would not be a base. But under the Bronsted definition, we can see that one of these hydrogens left water and went to the ammonia. So in this situation, the water acted as an acid and the ammonia acted as a base. The ammonia grabs that H plus from the water and makes NH4 plus, the ammonium ion. The water ditched that hydrogen, and what was left over was the hydroxide ion. And so the other thing that we can pull off of this is that under this definition of acids and bases, we will tend to see pairings take place. So, for example, water and hydronium, that is a matched pair. The only difference between them is the gain or loss of an H+. HCl and chloride, that's a matched pair. The only difference between the hydrogen chloride and the chloride ion is the loss of that H+. Same thing for the ammonia and the ammonium ion. They are a matched pair. And the water and the hydroxide, they are a matched pair as well. And so under the Bronsted theory, it's very easy, if you can pair up these matched pairs, to figure out where that hydrogen is going and where it is being left behind. Because you can look at the matched pair and say, okay, what is the difference between NH3 versus NH4+? Well, the NH4+ has an additional H+ ion. So that must mean that the ammonia, the NH3, was a base. Because the only way that you get from NH3 to NH4+ is to add an H+. And adding an H+ is base behavior. So it takes some getting used to. But we can eventually get ourselves to the point where we can recognize in any kind of reaction whether or not there's acid-base behavior being exhibited, because we should be able to see when and if those H+ ions are moving around. All right. There's one other property I want to point out here. Notice that in this particular reaction, water was acting as a base, but in the one on the bottom, water was acting as an acid. This is a property known as amphoterism. Amphoteric substances are substances that can act as acids or as bases depending upon their circumstances. As we showed in this slide, water is probably the most common amphoteric substance that there is. But other kinds of amphoteric substances exist. One of them is the bicarbonate ion, HCO3 with a -1 charge. We can see that in this situation, put it with a strong enough base like the hydroxide ion, and we can get that H+ on the carbonate to wander over to the hydroxide and make water and carbonate ion. Get it in a strong enough acid, and it can actually take on that hydrogen ion and form carbonic acid, H2CO3, which in a weird twist, this will usually decompose into carbon dioxide and water. Any of you that have ever done a baking soda and vinegar experiment know that reaction quite well. Baking soda, sodium bicarbonate, NaHCO3, the bicarbonate ion reacts with the acid in the vinegar to make carbonic acid, which spontaneously decomposes into carbon dioxide and water. And that carbon dioxide gas is what blows up the balloon or makes the volcano erupt, or, you know, pick your favorite baking soda and vinegar experiment. Whatever that gas is supposed to do, it's the carbon dioxide generated from this reaction that causes it to do what it's supposed to do. So amphoteric substances These are substances that have both acid and base properties to them. And what property shows up depends entirely on what the environment is. Put it in an acidic environment, it acts as a base. Put it in a basic environment, it acts as an acid. All right. Any questions about amphoterism? All right, let's rewind just one slide here. This particular phenomenon is much more common for acids than it is for bases. But what we see is that there are certain types of substances that can exhibit a multiplicity of their behavior. So in particular, we're going to look at acidic hydrogens. Acidic hydrogens tend to focus primarily on when we have usually organic acids of some kind. So if my acid contains a series of carbons, or in this case, we've got some kind of a polyatomic ion like the phosphite ion, your acidic hydrogens tend to be the ones that are attached to oxygens. So from this perspective, we have one acidic hydrogen and acetic acid. Even though there are 4 hydrogens in that acetic acid, notice that 3 of them are attached to this carbon. And if you recall, if we look at carbon to hydrogen as far as its bonding is concerned, these are non-polar bonds. And because of their non-polarity, they're going to be very difficult to break. They're going to be very difficult to separate. This bond between oxygen and hydrogen is polar. Oxygen is far more electronegative than hydrogen is. And so what happens is that we end up having more electrons kind of around this oxygen, and we can get that hydrogen to come off if we exert enough chemical pressure on it. So as a result, what we see here is that we've got really only one acidic hydrogen on acetic acid, even though there are 4 hydrogens in total. And in the case of phosphoric acid, this phosphorus to hydrogen bond, it is polar, but it's not nearly as polar as the oxygen to hydrogen bonds are. And so in the end, only those 2 hydrogens are actually acidic. So for phosphoric acid, we only tend to see, even though its formula is H3PO3, based on its structure, only 2 of those hydrogens are actually acidic, would actually give up ions. And so we have a name for that. It's called a diprotic acid. The prefix di meaning 2, protic being a derivative of proton, so 2 hydrogen. So the name diprotic acid indicates that it is an acid that has 2 hydrogen atoms that can come off of it. And so this is, again, this is far more common on the acid side than on the basic side, because especially with the acids, what we deal with there are lots of organic structures that happen to have an acid group on them. And as a result of that acid group, we can see that there are multiple places where that hydrogen can come off. And so what we have to do is we have to evaluate, and really what we're looking for structurally speaking are those OH groups. If we can pinpoint those OH groups, that tells us how many of those hydrogens are actually possible of coming off. Now, one other thing that comes off as a result of Bronsted theory here is the understanding that we don't need hydrogen or hydroxide necessarily to identify acids and bases. So if I look at sodium carbonate, for example, we know that when sodium carbonate dissolves in water, it's going to give us sodium ions and carbonate ions. That carbonate ion is actually basic. And under the Bronsted-Lowry definition, we can see how its base behavior comes about, because it is able to accept a hydrogen ion from water to form the bicarbonate ion and hydroxide ions. Since it is able to act as a base with water, then that means theoretically it should be able to act as a base with other kinds of materials, including things like hydrofluoric acid, where that hydrogen leaves the hydrofluoric acid, attaches itself to the carbonate, and again, forms the bicarbonate ion, and in this case, the fluoride ion. So in this case, no hydroxide are actually exchanged here, but we have an acid-base reaction nonetheless. We have something that is acting as a base, even though it contains no hydroxides. Let's wrap up today by doing a little bit of identification. All that we want to do is for these three reactions, identify the acid and the base. So in number one, I've got OCl minus and I've got water. Now, one way that I can do this is I can find the matched pair. If I look at that, my matched pair, OCl minus, hypochlorite ion, and HOCl, hypochlorous acid, are my matched pair. The only difference between these two is the addition of an H+. So under that definition, that means that the OCl minus had to have been a base. And if it's a base, then that means that the water had to have been the acid. The H+ came from the water to make the hypochlorous acid. In my second example, I've got H2SO4 reacting with fluoride. Once again, I can do this as a matched pair. H2SO4 and HSO4 minus. The only difference between the two is that loss of a hydrogen ion. That would mean that the H2SO4 is acting as an acid, and the fluoride ion is acting as a base. And I can do the same matching on the other side as well. I've got the fluoride turning into HF. So the fluoride was acting as a base in that scenario as well. So the way to do these, pick out one. It doesn't matter really which one it is. Pick out one and find its matching pair. And identify what happened to it. So I went from water to hydronium. To go from water to hydronium, I had to add an H+. That means that my water was acting as a base. My ammonium ion had to have been acting as an acid. I could look at the ammonium ion, see that it lost an H plus along the way, and arrive at the same conclusion that we had before. So that's section 1 out of chapter 13. On Wednesday, we will continue on by getting into section 2, talking about identifying strong and weak acids and bases. And we'll actually jump ahead a little bit and talk about buffers, which will help you out with lab. So if you have lab tomorrow, I'm sorry I didn't get that far with you. If you have lab later this week, it'll help a lot. Have a good day.